Good morning, everyone. Hello, am I audible?
Yes, sir.
Okay, uh, so let's wait for a few minutes and then we'll start. Okay, so anyway, you received the email about today's tutorial, right?
Yes, sir.
Okay,
Sir, I have some questions regarding the lecture.
sorry,
Oh,
you're not clearly audible.
okay, sir. Sir, I have some questions regarding the lectures.
Okay, so we'll start. I'm just waiting that if others can join. I will start at 10:05. Okay.
Okay, sir.
Okay, so let's start. Meanwhile, others can join. So, I am Sunit Das, a PhD scholar at IIT Kanpur, and I will be taking the tutorial of this course, Topology and Condensed Matter Physics, or Topology in Condensed Matter Physics. So, before starting, I think it is better idea just to tell about your courses or in which stream you are in. That will help me to navigate how we should go about these tutorials. So just unmute yourselves and yeah, tell.
Yes, sir.
So you are in PhD or MSc or what?
Sir, I am in MSc second year
Okay, where?
from Vishwabharati University.
Okay, fine. And Soma Sundaram, if I am correctly. So what do you do? I mean PhD or MSc? Okay, fine. Uh, okay, so we have this course Topology in Condensed Matter Physics, and this is a fairly advanced course in a sense that it was started uh, in way back in 1980s, let's say, but then the concept of topology in mathematics is even more older. It's pretty old actually. People realize the role of topology in condensed matter physics primarily from 1980s, and since then it is one of the most active area of research in, probably not in condensed matter physics but also in terms of physics also overall. It's 45 years of research. So in terms of tutorial problems, you will find that mostly I will solve the assignments which probably I am not supposed to solve. I will not fully solve those assignments, so that you should try it or yourself and submit it, because it depends. It is basically graded. It will be, but there are not much problems like you do in mathematical physics or any other basic courses, quantum mechanics or stat physics or so on, because this is a fairly advanced topic and this is a purely research topic. The course is also advanced, and the problems are also mostly based on what we encounter in our research or advanced understanding of condensed matter physics in terms of topology. We'll understand why the concept of topology and so on is required. Uh, so yeah, so as we go, we'll understand. But before that, let me ask few questions. That what is the expectation from these tutorials? That will be helpful for me, because as I have said that there are not much different kind of problem that I can do for you in these tutorials. The problems will be almost similar to the assignment problems. Okay, so what are the expectation from these tutorials? At least these will be helpful, because and these courses, or I mean the tutorial should be as much interactive as much possible, because this is a online course, so you are not getting opportunity to interact with the professor Saurabh Basu. Probably you had one, and you will have few more, maybe at max another one or two. So that's this is the only interactive platform that you have in terms of clearing your doubts and so on. So please feel free to ask questions, stop in between, and yeah, clear your doubts. I will try as much as possible. It's not guaranteed that I'll be able to answer every questions. I mean every questions of you. But yeah, you can email me at so I'll give the email address in the chat box, so that if you have any questions in between, you can email me and I will have a look before coming to these sessions. Okay, so the email ID is simply sunidh@itk.ac.in. Okay, so now yeah, so if you have any specific questions, please feel free to ask, or again the answer to that question, how should you go about it, this tutorial?
Sir, I have some doubts
Hmm.
from the lectures.
Hmm.
There, sir said that the topological invariant are remain invariant, just respect to the that how much hole is in it. If there is a one hole
Hmm.
and the things, the materials are, or samples are different, the Cherren number will remain constant. But in that case, there is h by e square, and
Hmm.
e is a electrical charge, I guess. So for various samples, the electric charge should be various. So then, how it is remain constant?
Okay. We'll see how it remains constant and how it is related to the number of holes. It turns out that in condensed matter physics constant, it's not really number of holes that we count. That's an analogy with the mathematics. That's the typical analogy. You will see a donut and a orange and so on and so forth. But again, it's an analogy. And in terms, so answering that question, that how the number of charges are same for different materials, it is not that the total number of charges are being talked here. Okay, it's just the electronic charge E, and that is constant, right? So we know that its value or magnitude is 1.6 into 10 to the power minus 19 C, and that's why it is important when you call it topological protection or topological index. It doesn't really depend on the how many number of charges are there, how many number of electrons are there in the bulk system. I may have a 5 nanometer by 5 nanometer sample where I have, let's say, huge number of electrons. It will be of the order of Avogadro or more than that actually, or let's say Avogadro number of electron density 10 to the power 21 3 per meter cube, let's say, if it is CD. If I have some other sample within the same topological class having uh, electron density, instead of 10 to the power 23, it's 10 to the power 20, it doesn't really matter. That's why it is interesting that the system's some property, again we'll see in detail why do we need this topological property and what sets them apart from the conventional phases of matter that we see or that we have read about from very early on, right? It doesn't really matter how many electrons are there, how many holes are there and so on. All it depends is some on the some characteristics of wave function and how the carriers behave because of this some twist in the wave function. Yeah, and that's why it is important that you forget about the minute details of the system. You take a topological class and you are just done. About that topology, you know that this is my topological index and this is how it should behave. Okay, so it doesn't really depend on the number
Actually, sir,
density.
in the
Hmm.
Actually, in the cases of resistivity, we usually do it how many number of carriers are there. That's why this question
Oh,
occurred to me.
this is a very good question and very relevant question, because I understand from where the confusion comes. Because if we simply think of Hall effect, the Hall coefficient or the conductivity, let's say, is sort of proportional to magnetic field by Ne, right? N is the electron density and E is the electronic charge magnitude, right? So you will typically think that Hall coefficient or Hall conductivity depends on the number density. So it should also matter in topology and topological index, but that sets them apart.
Yes,
That's why
sir.
we study topology, that it doesn't need uh, now how many number of electron density and so on. Okay, it is completely determined by something else. It's more of a wave function property. It's not about electron density and
Oh,
so on. So we'll see, because these things will clear as we go ahead in the within the course. Okay.
sir, there is another question.
Yes, sure.
Uh, that here, sir said that electron have a property like Mobius strip. Now, as he did the derivation, I got that, but I can't visualize it. Mat- I mean, how does it happen? I mean, the electron wave function after a rotation of 2 pi doesn't come back to the same point.
Right.
So I just can't visualize it that how it is happening. I know how Mobius strip work, but In the case of electron, how it is happening, I
So
just
you are
can't
saying
get it.
electron in solid state physics, right? I mean, condensed matter system,
Yes,
how
sir.
they are being the analogy comes. That's actually have to do with the Brillouin structure. So you have done solid state physics basics course, right? MSc condensed matter physics or solid state physics, whatever it
Yes,
is.
sir.
So there is a concept of Brillouin zone where the zone edge, let's say minus, if I think of simply 1D Brillouin zone, then it's the edges are at minus pi by a and pi by a, right? And minus pi by a and pi by a are essentially invariant point. So they are basically same point up to a reciprocal lattice vector G. So if you start from minus pi by a and go to pi by a, you are essentially coming back at the same point, right? And in between there is a different point. So if you are at from starting from minus pi by a and at 0, then you are not at the same point. But then if you again come back to the pi by a, you are back at the same point. So minus pi by a is basically equivalent to pi by a. So that's how we bring the analogy. We will see in more details that how this happens. Just a second, I need to take this call. Sorry about this. Hello. Hmm. अच्छा. হুম. আচ্ছা. তাহলে আর হুম. দুরন্ত আছে. দুরন্ত কোথায় আছে? মানে হাওড়া? হাওড়া দুরন্ত তো চাপ লেগে যাবে. অ্যাকচুয়ালি ওদিক থেকে আসা মুশকিল আছে একটু. ও অল এসি এক্সপ্রেস নাই? থার্ড এসি বা সেকেন্ড এসি বা ফার্স্ট এসি? আচ্ছা আচ্ছা. হুম হুম হুম. আচ্ছা. তৎকালে কাটলে আর পয়সাও ফেরত পাওয়া যায় না? আচ্ছা, আমার অ্যাকচুয়ালি একটা 23 তারিখে, সরি 25 তারিখের আছে দুরন্ত, কিন্তু পাঁচ পাঁচ ওয়েট লিস্ট হয়ে আছে, আমি বুঝতে পারছি না কী হবে. 25 তারিখ. তাহলে থাক, তাহলে ওটার ভরসাতেই যায় নাকি, হবে তো মুশকিল হয়ে যাবে. ঠিক আছে. Okay, sorry. So we are talking about, yeah, so the Brillouin zone and so on. So we'll see how it goes. So these things needs a little bit of more calculation just to see how things are being equivalent to the Mobius strips and so on. Okay. And there is another point, the lecture 4 is about tenfold classification, okay, and that is probably not, I mean, it is not a right place to read about those tenfold classification. I think we should read about it after the Kitai model, Haldane model, topological insulator and so on. Okay, so it has been clubbed to the lecture 1 series, but I think it is no, I mean, you will not get it unless you read all of those topological insulator, SSH model and so on. Okay, so you may skip it, and if you see there is no question from that lecture 4 in the uh, assignment 1. Okay, yeah. So any questions? Okay. In topological insulator, how to confirm the time reversal symmetry protects the edge states. This actually needs calculation, and the simplest topological insulator you can think of in terms of experimental realization, it is of course that quantum Hall insulator. very high magnetic field applied in a perpendicular direction to a 2D electron gas. But otherwise we can I mean from a theoretical point of view or more easy to understand language, we study SSH chain. Okay, and in SSH chain it will be actually clear that how this time reversal symmetry protects the edge state. I'm sorry, I cannot give a very well defined answer to these questions because each of these questions need explicit calculation to understand it actually. Okay, otherwise it will just be purely qualitative, which will not really help much. So we can do it, and that's why I'm asking ki, how should you go about these topics, because essentially the problems will be from the assignment itself. So should I be focusing more on the problems or these concepts, small concepts that sometimes is missing in the lectures? It is mostly clear actually, but yeah, lectures are within 2 hours, so or on our lectures, so yeah, few things might miss. And then second question is there any book regarding TRS and other symmetry relevant to topology and condensed matter physics? There are quite a few books actually. It's not about TRS. Whenever we study about topology and condensed matter physics, every symmetry comes into the picture. It's not so TRS is definitely one of the most important symmetry, but then parity symmetry or inversion symmetry, and then charge conjugation symmetry, and then chiral symmetry. All of these are important. And when we talk about topology and condensed matter physics, everything comes together actually. In fact, the tenfold classification is based on a number of symmetries: TRS, charge conjugation, spatial inversion, chirality, and there are few more. Okay. So there is a one book by topological insulator by Barnevik and Hughes. So that's one book definitely. And let me connect to the iPad and then write the name of the book. Okay. I hope there is no echo now. Okay, so there is one book by simply the name of the book is Topology and Condensed Matter Physics. Okay. Uh, so the authors are Bhattacharjee, MJ. So Somendra Mohan Bhattacharjee, Mohan MJ, and then Bandyopadhyay, Abhijit Bandyopadhyay. And there are quite a few review articles also that also can be read. So simply another book is Topological Insulator and something. By Barnevik and Hughes. And there are a number of review articles also that I will list. Okay. So any other questions, or so I'm actually seeking how should we go about it, because I can solve the problems, that's not a problem, but I found that the problems are also from the lectures itself, right? So this will be a sort of repetitive. So what do you think of these courses? I mean, how should we go about these tutorials? So should I be solving only problems, or cover some concepts? Hello, am I audible? Hello.
So,
Hmm.
I'm saying that it will be helpful if you cover some of the parts because this thing is totally new for me. So, it will be helpful.
Okay. So another, so Soma Sundaram. So what do you think? So my request is ki please be interactive. Otherwise, okay. Lectures are pretty good actually. So I am not sure that I will be covering something out of the lectures. But what can we do is that we can be more elaborate, because lectures are sort of designed to finish in within 2 months and so on. Uh, so yeah, mostly it will be within the lecture itself, and the lectures are pretty good. I am doing his tutorial. I mean, so Professor Saurabh Basu from 3 courses, and I mean, before coming to this tutorial, I watched his lectures. I found it to be pretty interesting and pretty good. But yeah, some concepts sort of was in a hurry, so we can uh, say few more things, or do explicit calculation that few steps have been missed in the lectures. Okay. And any confusion or any problem in solving the assignments, first assignments? I think the due date is 26th of February, right? So
Yes, sir.
you guys are able to solve the problems of the assignment.
Sir, I didn't start yet.
Okay. Okay, fine. Okay, so where is the cheat code? I am telling you. Every problem has been solved within the lecture itself. If it had not been solved, the clue has already been given within the lectures itself. So if you think carefully a little bit, it should be done actually. It's pretty much straightforward. Most of the problems are. Okay, and few problems have been thoroughly solved. It's not partially solved, thoroughly solved. So you'll find it useful. Okay, and do watch the lectures before coming to these tutorials. Okay, that will be much more helpful. We'll I'll tell about more books and reviews, or few notes that is there available on the internet freely as we go along. Okay, because writing all the books in a row is not something probably is going to be much help, because I'll teach something, or I'll deliver something, and relevant portion I'll give some reference from which I am following, but primary reference is going to be Saurabh Basu's lecture. Okay. So since it's a fast day, so let's start with little bit of introduction to topology and condensed matter physics. So yeah, and please feel free to ask questions whether in the chat box, or just unmute yourself and yeah, ask. Okay, so let's ask these questions. What is the phases of matter? So phases of matter is something that is set by some properties of the materials. Okay, meaning there are different phases of matter. If we simply think what are the phases of matter, the simplest way to think about it is there are solids. So one is solids, and second is liquid, and third is gases, right? And you can call it, there is definitely a fourth one, plasma, but let's not go into great details of these things. Okay, but primarily these are the phases of matter. And how do we say that these are the different phases of matter? Anyone? Again, if you think simply, then solids have a rigid structure. I mean, it has some kind, it got some kind of structure, and it is rigid, right? And liquid, you have some water in a bowl or something. It takes the shape of the container, right? And then gases are also similar. It has no shape actually. They are very apart. In fact, I should draw more. Okay. Now, these are sort of very layman's language to differentiate between solids, liquids, and gases, which is okay, which is understandable and intuitive. But then, in terms of physics, what is the difference between all three phases of matter, solids, liquids, and gases? One of the ways is just to what happens if you give shear stress or shear strain? Shear stress means, so this is the surface, right, upper surface, and you give a stress or pressure.
Sir, I think your screen sharing is off.
Okay. Uh, I can see my screen actually here. So, can Soma Sundaram tell that, are you able to see the screen?
Sir, now I can see too. Actually, maybe there was some network issues
Okay.
in my side.
Okay. Okay. So, okay. ठीक है. So, if you put pressure along this surface, let us say upper surface, then it is not going to change shape up to a certain limit. Of course, if you go over the threshold limit, then it will definitely tear and so on. But so it can withstand, or it is able to withstand this amount of pressure, a certain amount of pressure, right? It is in the solid shape is not going to change. So, this is shear strain, let us say. And if you give a shear strain to the liquid, so you have some liquid, let us say, and you somehow give shear strain, then liquid is going to change shape and it is going to slide kind of thing, right? And gases are even more trickier. You cannot really give simply this kind of shear strain, and it is highly compressible. So, so the interatomic forces between the atoms, or let us say ingredients in the solids, are much more higher. So, interatomic or yeah, so interatomic forces are much more higher, and they are highly dense in a solid state system. Liquids are somewhat apart, I mean lesser interatomic forces or inter ingredient component forces, but it is still dilute than the solids. Okay. And gases are even more dilute. There are very, I mean the interatomic forces are very small, so that they are hovering around all over the places. Okay. So, that is how you differentiate one of the basics phases of matter, solid, liquid, and gases, right. So, these are sort of, you can think of classical phases of matter. We all studied thermodynamics and so on, just to differentiate between these phases and how we yeah, how you study these, right. So, one of the main ingredient of all three phases of matter is the density. So, solid usually have very high density, and liquid have lesser than the solids, and gases have very low density, right. So, so here one of the key property that distinguishes these solids, liquids, and gases are these densities, okay, of the materials. So, this was sort of classical phases you read in basic thermodynamics course, and then there are other type of phases which is determined by, let us say, symmetry and order parameter. So, here also we have some kind of order parameter, but more tricky situation happens when we have some kind of symmetry and order parameter. For example, the simplest example would be magnetism. Okay. And this magnetism is not something that you need a solid to show it. Some liquid also show magnetism. So, what really happens is that magnetic moments are aligned along some direction, let's say. Okay, all the magnetic moments within a domain of a magnetic materials are aligned along the same direction. And then you all studied probably the basic StatMech course of Landau theory of magnetism, right? It turns out that in these phases, when they are ordered, there is a symmetry, and then when there is no order, there is a symmetry broken. So, this essentially symmetry governs these phases. Okay. So, for magnetic systems, it is the time reversal symmetry, TRS. Okay. So, in the magnetic phase, a material or magnetic material have broken time reversal symmetry. When these are disordered, so I have magnetic domain all around this, so that they average out to 0. Okay. So, then it is so this is TRS broken, and this is TRS preserved in non-magnetic state. So, this is magnetic state, TRS preserved. So, we will also see how TRS as a symmetry operator behaves. It is not something that we usually encounter, it is an anti-unitary operator. Okay. And we in Landau theory, we simply studied in terms of Landau free energy, where it was sort of A m square, m is the order parameter here, plus b. I am not caring about sign and a by 2 or b by 2 and so on. Simply everything is included in this a and b coefficients. So, m is the order parameter. Okay. In the magnetic states of a material, m is simply 1, or it can be below to 1, but some finite value, it got some finite value, and in the disordered state, m equal to 0. So, that is how we define order parameter. In a certain ordered states, it has got some non-zero value, and in disordered state, or the symmetry preserved states, in this case TRS symmetry preserved, it is 0. It can also be minus 1 actually, because if you remember, the Landau free energy was a shape of something like this, right. So, this was the free energy and this was the m. So, these are the two ground states. So, this is plus 1 and this is minus 1, okay. And there is sort of infinite amount of energy cost, or not infinite, this amount of energy cost to go from this to this. Okay. So, these are two ground states, where this is m equal to plus 1 and m equal to minus 1. So, these are the phases of matter which is not we cannot distinguish these phases of matter, or to study these phases of matter, we need the concept beyond solid, liquid and gas. So, here it is symmetry and order parameter, and then Landau theory explains it pretty well, right. Uh, so, so you already get an idea that depending on the which properties of matter we are talking about, there are different phases and there are different ways to classify things, right. So, in terms of first classical phases, we talked about solid, liquid and gases. There we talked about the property of density, right. Solid has a very high density, liquid has a sort of low density than solids, but still quite high than the gases, and gases are really low density of particles. In these classical phases, so let us write it classical phases. So, this was the density that was determining it. There are other things that we can think, you are giving shear strain or shear stress, how much it can withstand or not, and then there are symmetry and order parameter that was determining the phases of the system. When we talk about some magnetism or similarly ferroelectric materials, same thing in magnetization. Magnetization is the thing that we talk about, order parameter that we talk about in terms of magnetism, or polarization is the important quantity which determines the ferroelectricity and so on. Basically similar thing, one determines the magnetism, one determines the ferroelectricity. Okay. And different so the symmetry of the system and the order parameter was dictating the properties of these materials, whether it is a magnetic or non-magnetic, and so on, right. So we can classify matters and so on depending on which property we are studying, right. So just to tell you more about it, so a liquid can also be magnet, so and non-magnet depending on the Curie temperature and so on if it's a ferromagnet. So you initially classified as classical phases of matter, you are in the liquid, let's say, or let's say solid state. I mean, since we are more we will be talking about condensed matter physics. So we classified depending on the density, that this is my solid state system. Now you are classifying the system again depending on the magnetism, that it is non-magnetic or magnetic, you have a order parameter or not, you have a time reversal symmetry broken or time reversal symmetry preserved. uh, all of this is fine. Then the question is, why do we need topology? So topology basically is a phase of matter similar to this kind of, actually not similar to this kind of, that's why we are interested in this course. But the key idea is to classify and distinguish different phases of matter. uh, so that's where the topology comes in, that few materials in terms of few properties. Okay, every time we talk about phases, immediate question should be in terms of which properties that we talk about. Okay, so in terms of few properties that we will see in this course, it cannot be described by the whatever knowledge we have, classical phases or symmetry, broken state, Landau theory of magnetism and so on. It cannot be classified all of these known existing theories. It can only be classified, or it can be only understood something new, which is topological index and topological protection and so on, and basically we club all of these terms in topological properties. So topological properties are nothing but few index that we count, or topological invariant that we say. So let me write. Topological invariant. So similar to other cases, classical phase and symmetry broken phases, here the topological invariant is the quantity that determines the topological classification. Okay, so we can have so topological invariants are basically Chern numbers. We will see each of the examples actually, and then Z2 topological invariant, and then actually before that, before Chern number, I should have written winding number. Okay. So these are the primarily three topological index, and there are many other actually. So when we talk about topological classification or topologically distinct materials, then we are definitely talking about one of these, and there are many others, but let us say these are the three uh, topological invariant or property that we have. So we talk about Chern number 0 or 1, or it can also be 2 and so on. It has to be integer. Same with the winding numbers, same with the Z2. Z2 is sort of 0 and odd, it can be. So so you see little bit of similarity between this symmetry broken phase in terms of magnetism, that these are the different topological phases. Okay, m equal to 1 and m equal to -1 is basically similar phases. They are sort of so they have similar property. Magnetism is there in the both the cases, but there is more gauge invariant, I mean gauge phase and so on. Okay, but those are details we will not involved in. But so if you think about these two cases, m equal to 1 and 0, this is the quantity that is determining that my system is magnetic or non-magnetic, right. Similarly, we will have something called topological insulator, where Chern number will determine the thing, or winding number determine that it is a topological insulator, I mean topologically non-trivial cases or topologically trivial cases. So topologically trivial means it is just not topological, okay, and non-trivial means it has got some finite topological invariant, might be Chern number, winding number, Z2, depending on the symmetry of the materials and other details of the materials. And definitely these topological phases let us say topological insulator. So, if we talk about, I will tell briefly that what topological insulator is, and we will explicitly solve one of the problems, SSH model. Things will be much more clear when you study SSH model. Okay. So, topological insulators, and it are so it has got in something interesting that, so let us say we have a 2D sample, okay, and topological insulators are primarily, by the way, 3D. So, let me draw it. Okay, something like this. Okay. Now, in the bulk, so if you are sending some current or electric field, let us say you have applied some electric field and you are measuring some voltage between these two opposite Hall voltage, let us say, or anything, you can also measure longitudinal, that is not a problem. You see that the bulk of the material is insulated, okay, and the only conduction happens through the edges. So, so if I make a 2D version of it for simplicity, so all of these states which is well within the boundary is not going to conduct. What conducts is that these boundary, okay. So, this boundary conducts electricity, and then bulk is sort of insulator, it is not conducting. So, we talked about conductivity. So, based on conductivity, we again divide condensed matter system into 2-3 system, I mean 2-3 categories depending on the properties. So, so before going to that, if you have any questions, please feel free to ask. So, any questions so far?
Hello, sir.
Yes.
Sir, actually, from TRS, there is a thing sir did that the complex conjugate is equals to time t. So I didn't get that that how it is coming. So if you can elaborate a bit, it
Okay, so
will be helpful.
I'll come to that once I finish these things. Okay. Okay, so actually before
Okay, sir.
coming to this topological invariant and topological thing, after this symmetry broken phases, I should have talked about the classification of even condensed matter physics itself, depending on the conductivity. Okay, so let's do that first, and then I will come to your questions. So, let us say we have a solid state system, and you are trying to characterize the system based on how much it conducts electricity. Okay, so you apply, so you have a system and you apply some current in the system, and you are measuring the voltage that that it is conducting at all or not. Okay, you can measure also the Hall voltage also, does not matter. So, depending on the how much easily it conducts, so we have a so let us say conductor, and then semiconductor, and insulator. There are other phases also, but these are the again primary 3. So, in conductor what really happens is that, so you must have seen this kind of band picture, right, uh, in the basic electronics course, let us say. So, these are the bands. So, this is the this one is the upper bands, let us say blue, and then this one is the lower band. So, this is let us say conduction band or upper band, first band, and this is the second band, and these bands overlap with each other, right. So, once you apply electric field into this kind of system, they because of this force F equal to minus E electric field, the electrons gets easily excited and then starts conducting electricity. So, that is the conductor, and semiconductor is something that you have a small gap in between. You need to I mean give electric field beyond certain level, or you are creating, sometimes you create junction and create depletion region and so on and so forth to just make it conducting, right. So, basically these are small gaps, so that small amount of electric field or any other perturbation will starts conducting. Okay, so electrons or holes from here, it can go to another region, and the electron flow will be there, so that there is a conduction of electricity. Insulators are something similar, but then they have a very high energy gap. Okay, high energy gap, so that you need a very high magnetic electric field, or in fact in general when we talk about insulator, we typically say that these are not something that conducts. Actually, if you apply electric field, there will be no conduction that is happening. So yeah, so these are the primarily three things: conductors, semiconductors, and insulators. When we talk about solid state system, based on the properties, how it conducts electricity, how much easier it is for to conduct electricity. Okay, and when we talk about topological phases of matter, all of these can show topology. Okay, but that is based on the topological invariant that we have, that we will talk about later. Okay, so this was sort of very brief introduction to topology in condensed matter physics. It was not a very well designed introduction, but the idea was to give motivation that why should we study topology. We all have been studying different phases of matter depending on the different properties that we look at. Topology is something that we will look at very detailed, and in terms of topological invariance and so on. Okay. So yeah, what was your question? Can you please repeat?
Sir, in time reversal symmetry, sir demonstrate that time is equals to complex conjugate, and there sir mention some properties like T ck T inverse equals to T sorry T ck T inverse equals to C minus K. I also don't get that too. I mean, how these transformations are happening and the things.
Okay. Uh, okay. So basically, when we call it time reversal symmetry, in simple terms, we say that t goes to minus t, right? That's what we simply tell. But we cannot go back in time. Forget about those relativistic possibility and so on. We are not concerned here about those things. Okay, we are studying condensed matter physics. When you say time reversal symmetry in condensed matter physics, what it essentially means is that a particle moving with velocity v, let's say, along some positive x direction, and the same particle moving in minus x direction, let's say, with some velocity of course v, minus v, because of it is a vector quantity, how their properties are same, or are they moving exactly like this one and this one. So are these exactly equivalent or not? If these are exactly equivalent, moving in plus x and moving in minus x, then we say that the particle has time reversal symmetry. Okay, but in terms of mathematics, we can call it, okay, t goes to minus t, so that's what it means in terms of time reversal symmetry. Okay, now let's see what are the quantities that changes under time reversal symmetry. Okay, so let's start from a simple r operator or x, if we confine ourselves in to 1D. So this is, let's say, time reversal operator. Okay, so time reversal operator acting on, let's say, position, simply position, it changes actually nothing. Okay, it goes to x simply. Or so actually in mathematics, strict mathematical term, we do not write like this t, sorry, t goes to x, I mean t x goes to x. Actually when we say invariant, we write it like t x t inverse. So you complete that operation on x, and if it stays same, then we say that it is invariant under time reversal, or that's any operator. Okay, so the position do not change under time reversal, and velocity, if you operate on velocity t inverse, it goes minus v, let's say. So if you give vector. Why? Simple way to see that velocity, if simply we can think of dx dt, right? X doesn't change sign, but t changes sign. So, basically velocity also changes sign. Similarly, other thing we can also prove, let us say what are the other quantity that kind of changes sign. Linear position, velocity, and okay, next thing is obviously the angular momentum, let us say. So, let us say we are concerned about z component of the angular, or we can simply write velocity vector also, does not matter. This also goes to minus L. So, angular momentum also goes to minus L. So, L is what? L is r cross p, right? P is the momentum. So, again simply classical terms we can think of L equal to r cross mv, right? M is the mass, it does not change, it is an intrinsic property. R also does not change. So, again V changes sign, right. So, that is why L goes to minus L. Now, that is how we determine that time reversal symmetry changes the sign of a operator, or I mean a quantity or not. Now, we are talking about C j of, let us say, k argument. Okay. How does it behave, right? How does it behave, or any other so this Cj is definitely the annihilation operator that we are talking about in the momentum space, right. So, since V changes sign, or in general momentum changes sign, so we are just multiply by m and it will be momentum, right. So, under time reversal, momentum changes sign, okay, p goes to minus p, and P is definitely h bar of k. In solid state case, we call it, we write it as h bar of k, okay, and k is here block momentum. So, if you take periodic systems and so on. So, let us say we have this Cj annihilation operator, and we want to see how this behaves, right. So, it turns out that it will be Cj of minus k. Why? Because we know that k is going to minus k, right. From this expression, T of k, T inverse is going to minus k, and time reversal operator is not going to change the creation to annihilation and so on. Okay. So, a particle is here, it is not going to be annihilated or created by just by operating time reversal, right. It just reverses the direction of the motion for the particles, it does not annihilate the particle or create the particle. Time reversal symmetry does not do that. Okay. So, for that we may have different operators. In fact, C dagger and C itself does that. That C dagger acts as if like it creates an particle here, and C annihilates this particle here. Okay. It has got some index where it is acting. J is, let us say, the real space index. So, since it does not affect on the creation and annihilation operator, that is the physical or intuitive way of thinking. So, it should not affect the Cj, okay. But then k goes to minus k is already there, right. So, this we need to take into account, that k goes to minus k. In fact, for any operator, any general operators, let us say A is a general operator, or O is a general operator, it has got some function of let us say, so f1, f2, f3 are the quantities. Okay. So, this is a some general operator, f1, f2, f3 are some quantities that is that determines the general operator O. If I want to do T inverse of that, or how this general operator changes under time reversal, we need to see what this operator really is. Okay. So, why should it change sign or not? For example, angular momentum was changing a global sign, right. So, that plus can be plus or minus. If it changes sign, we will put plus or minus, and then of course, that operator, and we need to take care into of the fact that f1, f2, f3 changes sign or not under this. So, we need to see individually f1 T inverse. So, does it change sign or not? Okay, these are not, definitely it will change sign. So does it change sign or not? Similarly F2 also, and so on. So so that's how you get Cj goes to Cj of minus k. You cannot say that it is Cj of k only. Okay, time universal symmetry doesn't create or an let's say property, I mean particle at some point, but its argument can be changed, depends on uh, the argument itself. So here k goes to minus k. So similarly if we take another example, let us say time reversal operator Cj, j is some index in the real space. So I have a 1D lattice, let us say, and here you are annihilating this particle, jth particle, let us say, okay, determined by Cj of x. So this is along the x, let us say. So Cj of xj, I can say. So Cj of xj and inversion. So how does it change under time reversal? It turns out if you are in the real space, it doesn't do anything. Why? Because x doesn't go to minus x under time reversal, right? Here, sorry, here. So that's how you determine how it changes under some operation. Actually this is true for any operation. For time reversal this is the case. For momentum space you need to change the sign, or real space it is same as previous case. So is it clear?
Yes, sir.
Okay. So any other questions? Please feel free to ask questions, otherwise so as I said, this is the only interactive session that we are having. Okay, so no questions. Okay, so I can solve few problems, let's say, or what should I do? So the concept of these courses are pretty long actually. So what I intend to sort of teach, or at least I want to cover SSH model in a bit detailed manner, and how this normal insulator is different from topological insulator, how do we classify all of this. So that is the thing I think we should talk a little bit detail, but those in itself is a topic of I don't know 4-5 hours. So it so even if I do SSH model in details, it will just take 2-3 lectures in itself. So I'll try to be brief, so that maybe 1 or 2 lectures we can finish SSH. Okay. Okay, so let me give some hints about solving those assignment problems. Okay, uh, but again, these are something that you sort of know of. It's nothing absolutely new. So let me open the assignment itself. So you're able to see which screen actually. Uh, okay, so you will see only my whiteboard. Okay, so the first question is, let's write question 1. Okay, so the first question is, using Gauss-Bonnet theorem, find out the Euler-Poincare characteristics of a sphere and a torus. Okay, so what is the Gauss-Bonnet theorem? Gauss-Bonnet theorem simply says that uh, K, or this is rather kappa actually, dA is the elemental surface area 2 pi chi of r. Okay, and this chi of r is sort of Euler Poincare characteristics. You can think of this as a topological index. Okay, a similar, a very similar expression you will see in terms of Chern number. Okay, so just to write, I'll explain later. Chern number has also this form 1 by 2 pi uh, omega dot ds. Okay, here omega is the Berry curvature and ds is the elemental surface area. Okay, so here k is the actually the curvature term here, and dA is again elemental surface area, and there, so you see this is Chern number and this is Euler Poincare characteristics. Okay, so we have a sphere, and so first case is the sphere and the torus. Okay, so we have a sphere, and okay, so another point is we can write k dot dA as something like 2 pi into 2 minus 2g. Okay, so this we can write, so this is actually a purely mathematics formulas, mathematical formulas, meaning it is actually coming from the mathematics to differential geometry and so on. So G is the genus. Genus you can think simply as a how many number of holes are there in the system or in the object that we are talking about. Okay, so this is just to simplify. Chi r is the Euler Poincare characteristics, and you are just directly you can relate it to the genus by this expression 2 minus 2g. So a sphere, since we are talking about solid sphere, so it has got no hole in itself, right? So so the genus or the number of hole for this sphere is simply 0. So this means is that k dot dA equal to 2 pi into 2 simply. Okay, okay, so basically this chi r is defined by chi is defined by 2 minus 2g. So in our case Euler Poincare so sphere, let's say Euler Poincare characteristic for a sphere is simply 2. Okay, just a minute, I think I am creating a problem with 2 actually. Actually in general we call it as 1 by g, 1 minus g, not 2, just take the common. So then if g is 0, then it is simply 1, right? Similarly a torus is something like, how do I draw it? So it has got some structure kind of toroid that we studied in electrodynamics, right? So you have a so you simply think you take a A4 sheet page and you make it or fold it like a cylinder, and then you connect the two edges of it, right? So two flat edges you just connect it. So that's how you create toroid, and of course for toroid you sort of uh, give wiring to it, winding to a wire, but this is what we call it torus. And this is a very important object in case of topology, because you can think 2D Brillouin zone, we will see how it goes, but 2D Brillouin zone is actually a torus. Okay. So, torus is a topological object, because you will see so chi for torus will be, so here G for torus is what? So, how many number of holes are there? So, there is a single hole here, right. So, G is 1 here. So, chi torus is 1 minus G equal to 0. Okay. So, so that was so these are the answers for first question, and you will see similarity happens with this torus structure to the Brillouin zone of a 2D system. So, we have a 1D system, let us say. This is how the Brillouin zone boundaries are. A is the lattice constant, let us say, somewhere here 0, and then this is pi by A. Now, since these two are related by reciprocal lattice vector G, so they are basically equivalent up to reciprocal lattice vector. So, pi by A is equivalent to pi by A plus minus G, let us say. G is some reciprocal lattice vector we have. So, G for 1D, this case will be simply 2 pi by A and some vector direction, let us say. Okay. So, this is mod G. So, okay, we are in 1D, so we can think of x. So, so since these 2 points are equivalent, we can think these are sort of joint, right. Now, you take a 2D sheet, a 2D Brillouin zone. A 2D Brillouin zone look like a square, right. So, again you have 0 point here, or rather the 0 point is here. Along x it is plus pi by A, along minus x it is minus pi by A, and same thing for y also. So, you touch these points pi by A and minus pi by A, sorry I should, okay. Yeah. So, so you fold this point minus pi by A and pi by A, and you are also attaching this point or connecting this point. So, you will get a similar torus kind of shape. Okay. So, that is how it got importance in case of Brillouin zone also. Okay. So, we will see all of these examples in more detail when we do SSH model, and another one is just very basic introduction to 3D topological insulator. Okay. So, second question is, find the general form of Berry phase for a Hamiltonian H lambda. Lambda is a parameter that depends slowly on time. So, this is actually derived in detail, I think in lecture 2 or 3. So, I will not derive that, and in fact another good I mean source to read this about this Berry phase of Hamiltonian is just the Griffith's basic quantum mechanics. So, we will have a chapter something like adiabatic evolution, okay, or adiabatic approximation maybe. So, in that chapter it has been derived in detail. Okay. So, the next question is, explain why time reversal unlike most other operations in quantum mechanics is an anti-unitary operator. Okay. So, this has also been actually derived, or I mean explained in the lecture itself. Okay, actually, so I will not waste time by doing this again, because things are already there, right. I'll briefly tell about the second question, which is you just need to apply the time reversal operator to a hydrogen wave function, let's say. So the question is, consider a hydrogenic wave function yml. So this is the wave function, and we need to so L is orbital, M is angular spin angle. So these are both orbital angular momentum operators, or I mean characteristics, so rather angular. Okay. So the question is, how does the wave function evolve under time reversal? Okay. So we need to find yml of theta and phi, and T inverse will be what, right? So if you see the structure of yml, so you will have lot of it depends on the L and M, but okay, it is proportional to minus 1 to the power m, and then e to the power I m phi, and there are corresponding to L there are a lot of complicated functions, right? So it is associated with the PL. If I take the parameter as x, so it is x, right? Associated Legendre polynomial, etc. But more importantly, I mean, what is going to change here is that under time reversal, you have this I part, iota part, right? Other these terms are sort of for one case it is 0, p when L equal to 0 it is 1, and then x, and then I think L equal to 2 it will be 3 x square minus 1, something like this, right? And there are some normalizer constant in terms of factorial, L factorial, 2 to the power L, and so on and so forth. All of these are real, but the most important point for this time reversal is this one, e to the power I phi, let's say. Okay. So e to the power I phi. So under time reversal, so e to the power I goes to minus I. So all the other parts remain same, whatever we had, let's say, for this PL and so on, and minus 1, sorry, minus 1 to the power m remains minus 1, and e to the power I m phi goes to e to the power so e to the power I m phi goes to e to the power minus I m phi. So I under time reversal I goes to minus I, okay, and then the rest t minus 1. Okay, actually this will be the when you operate it. So all of these orbital part let's say, orbital part corresponding to L remains same, minus 1 to the power m and e to the power minus I m phi. So L part remains L, but you just can think that m goes to minus m, let's say, so minus m L. Okay, so that is the operation. Okay. So next question is, again it has been discussed. Yeah. So all of these questions actually discussed. So let's take the example of 5. Let theta be the expression for time reversal symmetry operators. So Okay. So assume theta is the expression for time reversal operator. So we are so far talking about t as time reversal, but it is equivalent to theta now. So that for a spin half particle theta square equal to -1, whereas for a spinless particle theta square equal to simply +1, and then explain the Cramer's degeneracy. Okay. Okay. So again, if we come back to these so these time reversal operations, let's say here that we talked about, uh, so so x goes to minus a x goes to a, v goes to minus v, and l goes to l, and so on. So what it really does is that in general it does complex conjugation. Okay. So for so this was the case for spinless particle. So we are not defining or not characterizing the particle, I mean spin of the particle. So spinless particle. And there is another way to see this ck goes to minus k actually. Okay. So where it was, so this one ck goes to minus k. So ck you can write in terms of Fourier transform of cj of k, right, e to the power I k dot r, something like this, right. So integration with respect to r. So cj doesn't change a sign, because as I said x doesn't change sign and it cannot create or annihilate particle, so it doesn't do anything on cj time reversal operator. So you need to simply do k goes to minus k, I mean I goes to minus n, k goes to minus k. Just a minute, that's how you cannot say actually, because both changes sign, k goes to minus k and I goes to minus a. So this is not the right way. Okay. But anyway, so the crux of the story for time reversal symmetry for spinless particle is that these are the quantities that should not change, x and cj in the real space, and then in the k space it goes again remains same, but k goes to minus k and l goes to minus l, and another one is this iota. So I goes to minus I. Okay. So basically complex conjugation. So we can summarize this in terms of time reversal operator for a spinless particle as complex conjugation. Okay. And if we simply think for spinless particle, so t I minus T inverse is minus I. Now you again apply on this. So T square means you apply 2 times, right. T square operation means you apply the time reversal operator 2 times. So you got the result, and then again minus I and T inverse equal to again plus I. So essentially T square operation for I is what is going to give me again I. So we can think of there is a plus 1 in front of it. So the so theta squared, so T square eigenvalue you can think as plus 1, right, for spinless particle. Now for spin half particle or any actually this is only true for spin half particle, we can generalize it for other spin particles. For spin half particles T or the time reversal operator is simply given by I sigma y k. So k is the complex conjugation. So this you can derive, it has been derived in lecture 2 I think, that for spin half particle you need these Pauli matrices. Physically what is really happening is that spin up particle under time reversal goes to spin down particle. Okay. And why does it happen? Because spin got some intrinsic angular momentum, right. Spin has some spin angular momentum, that's what we know from Dirac equation or Stern-Gerlach experiment and so on. So angular momentum changed sign. So we had this relation angular momentum minus 1 goes to minus L, right. So this was the orbital angular momentum, we wrote it in terms of r cross p, but again it's the same thing in terms of angular momentum sense, that one is orbital angular momentum, one is spin angular momentum. So both changes sign. So that's why spin up goes to spin down, and this is the main distinction between spinless particle and spin uh, half or any other spinful particle, and you need to take accordingly the expression of time reversal operator, which takes into account of spin. For spin half, we will only concentrate spin half particles in our whole discussion. So for spin half, it is given by this I sigma y k. Okay, and if you do the operation, so T square I sigma y k and then I sigma y k. So you will get I square means minus 1 and sigma y square and then k k prime, sorry k k. K is just complex conjugation. Again you are doing complex conjugation of any proper, I mean any complex uh, object. Let us say a plus ib is my complex quantity, y equal to a plus ib. So you do two times of complex conjugation, right? So initially you have a minus ib and then again complex conjugation a plus ib. So it got no effect. So you only left with minus 1 sigma y square. Now sigma y square is unity, right? In fact any sigma square, sigma x square equal to sigma y square equal to sigma z square equal to unity, Pauli matrix property. So this is minus 1. Minus 1 means these are some operators, so you can think of it as a unit matrix. So for spin full particle or spin half particle, T square equal to minus 1. Okay. So then it is proved. And what Cramer's degeneracy is? Cramer's degeneracy is basically, so let us say you have a wave function psi, okay, of some Hamiltonian E psi equal to some H psi equal to some E psi, and now you take the time reversal partner of this psi, T psi T inverse. I am again using T actually instead of theta. Okay. So T psi T inverse you denote by psi T, let us say. So this is the time reversal partner of psi. Okay. Now if you have a system or if you have psi t such that psi t, h of psi t is again the same. Okay. So you had h of psi equal to E psi, and second is that h of psi t equal to E psi. So for both the time reversal partner wave function, the energy is same. Then we call it a time reversal, sorry, Cramer's degeneracy. So when we call it a degeneracy, suppose we have a band like this. This is corresponding to let us say psi, okay, and you have another band exactly overlapping on each other, okay, and this blue one is because of psi t. So these are degenerate bands in terms of energy. So both got same energy, but they belongs to different wave function. But what is important here is that these psi and psi t should be orthogonal. Okay. So the states are orthogonal to each other, but they have same energy. We can also think of like psi of t psi equal to 0. So time reversal operator inner product with the wave function is 0. That is the first, I mean second condition, and then the first condition is they have the same energy. If we happen to occur in this kind of situation, then we call that there is a Cramer's degeneracy happening, which have same energy, but the wave functions are time reversal partner of each other. Yeah, that is the two scenario depending on which we call it Cramer's degeneracy. And so what really happens for this kind of Cramer's degenerate particle or Cramer's degeneracy bands for spinless and spin half? So for spin less particle, you have energy as a function of k. Okay. So you all know the tight binding and energy, Brillouin etc. concepts, right? because in next classes, I mean, when we say, when we do SSH model and so on, we will extensively use those things actually, tight binding model and the band picture of electronic spectrum, etc. So you know tight binding models, right? Okay. So if anyone doesn't know, then let me know. I'll have a very brief overview what really tight binding model is. Not today, but some other day. I mean next class, let's say. Because the most important thing I think is that you understand something. That's how it will be better for you also, for me also, right? Otherwise, assignment you must need to solve. You definitely need to solve, but that is also, this is also important, that you get to learn something. So if you do not know, then let me know. So I assume that everybody knows tight binding model. Okay. Okay, so for spinless particles, the Cramer's degeneracy is sort of this kind, ek of minus k. Why ek of minus k? Because, so this is, let's say, one of the psi, and this is, let's say, one of the psi t, right, time reversal partner. Now under time reversal, k goes to minus k, again same thing. So basically psi t will be psi of minus k, and then corresponding complex conjugation and so on. Okay, that I am not writing. Uh, so you have a time reversal symmetry or Cramer's degenerate. The bands will look like, at k and minus k, the band energy are basically same. Okay. So this was for spinless. And then for spinful, or when you do spinful, we will only talking about spin half particles. So for spin half, so you have a band, let's say, at some k, and then that spin is sorry, the band is for, let's say, spin up particle. Okay, this is up particle. And what will it do for the when you operate Cramer's degeneracy, or I mean time reversal? It will just be k, I mean minus k, k goes to minus k, and up goes to down. Okay. So this is the form of Cramer's degenerate pairs for spin half particle. So let's draw. So you have a band something like this. This is like E of k for spin up particles, and then you have another band exactly overlapping on each other at each k point, but then it has got the characteristics of minus k down, let's say. Okay, so these things should be symmetric actually with respect to k and minus k, but it doesn't look like. So yeah, so actually so if you think carefully, it will happen that so you are, let's say, in the k, so you are, let's say, in the positive k, you have here the uh, plus spin at some energy E. If you go to negative energy, I mean sorry, negative k, you will have the same energy, but then this is for the down spin. Okay, that's what it happened. Okay, and these things are actually important. There are real life examples or real life systems of this kind of thing. Okay, so yeah. So if you have any question, please feel free to ask, or any doubts, let's say. So any questions? Okay, no questions it seems. Okay, so if you have no questions or doubts, then I think we can stop here for today, since it's a fast day. Uh, and the regular timing is, of course, Saturday 6 to 8, but again 1 or 2 days we can I may have to reschedule actually, because I will attend some conference, so might be problematic, so sorry for that. But in general it is Saturday 6 to 8 actually. Okay, this is not the actual timing. But since you are here, so what timing will be sort of convenient for you guys if I need to uh, replace or need to move some Saturday tutorial session? So is this timing okay or any other time? You please suggest. But I think there are a lot of participant registered, but uh, it's not coming. But okay. No, I'm talking about Saturday is fine. Okay, Saturday is the fixed day. That we are not changing. But one more day I may have to reschedule because I will be attending some conference actually. So okay, Sunday. Sunday which time? So I'm generally okay apart from few days, but that's so Sunday 6 to 8 is okay, right? The same timing as Saturday. Okay, fine. So if I may have to move, then otherwise it's okay. I mean Saturday is the fixed day. Okay. Meanwhile, if you have any questions or query, you can write to me. Okay, once again, just reminding SUNIT d@itk.ac.in. Okay, so this is the email address you can email me at, so that I'll have a look and yeah, we can have a discussion. Okay, in fact any so if you do not understand any part of the lecture series, let's say, or you want some more elaborate discussion on some part of the lecture, uh, you just email me beforehand, so that I'll have a look at the lecture also once again, and I can prepare accordingly some notes or some uh, yeah, some literature I can share with you. Okay, but do see or watch the lectures, and yeah, that's it.
Sir,
Yeah.
actually, I am doing my dissertation on this topic, topological insulator. So,
Okay.
can you suggest me things that can be helpful in my dissertation?
uh, Actually depends on what you are doing, because topology even in condensed matter is a very vast topic. So uh, I actually do not understand the question quite well, because what are you doing in your dissertation matters more. I mean, okay, topological insulator is
Actually,
one thing. Hmm.
I'm not started yet. Today is gonna be my first class. So just I am asking for some like research paper or notes from where I can prepare well for my dissertation.
Uh, okay, there are actually lot of notes and archive uh, sort of small articles are there, but one the best article for topological insulator would be by Barnevik and Hughes. It's a book and you will freely get it somewhere online, I know. But that's a pretty detailed book. Okay, lot of things have been discussed. It's not only about topological insulator. Okay, although the title is like that. uh, so that's the one thing you can start with. And uh, yeah, that's the one thing. And another thing might be uh, so there is a topological matter school, something like this. It is conducted by some university. It rotates basically in European Union. TU Delft mostly conducts this. You have a online lecture series on the YouTube actually, topological matter school, so you can watch those actually. Okay.
If I search on Google topological matter school, then I can get that.
Yes. In fact,
Okay,
you will get a
thank you,
lecture
sir.
notes, big lecture notes, 200-page lectures notes by Titus Newport, and Altman was also there, I think. Yeah. But again, so all of these are so this is a reading course or a research course, I mean research. I mean, there are two kinds of projects that usually happen, right? One is a reading project. I read something new, something state of the art happening now in terms of research domain. And there is something called research project, where I really need to find something new, or at least I need to move towards a new thing to do. uh, Success is not, I mean, success is not here. I i may not have the new result, but the thinking, some calculation or something will be along those lines. Okay.
Okay, thank you, sir.
Okay. Okay, so I'll stop this meeting for today. We'll meet hopefully on next Saturday. If not, then of course Sunday we'll reschedule. Okay. Okay, so I'm closing the meeting then.